Hi guys, today we're going to look at exercise 7.2, the worked examples from your Year 12 jacplus textbook, and it's anti-differentiation. So people are quite good at anti-differentiation, quite enjoy the applications of it, so it should be a good chapter. Let's look at the first one where it's just a basic anti-differentiation, and what we'll do first is think about how differentiation and anti-differentiation are opposite things to do. And the way I like to think of it is, well, let's take this 3x to the 4 here. If I anti-differentiate that, it would be 3/5 x to the 5, as you might remember from year 11, but if not, don't worry, I'll explain in a minute. And what we would do if we were going to differentiate, then we would say, well, multiply by the power. So we'd say 5 times 3/5, and that would give us 3x to the 5. And then the second step would be that we would subtract 1 from the power. So that would mean it would be 3x to the power of 4. So that would be if we were differentiating. To anti-differentiate, well, anti meaning going the opposite way, well, we just do the opposite thing in the opposite order. And you'll see I've done this little flow chart here. It's kind of similar, or actually it's really exactly the same as what you might have done in year 7 or 8, where you would have used flow charts to introduce yourself to backtracking with algebra. So if we're starting with 3x to the 4 and we go backwards, we're adding 1 to the power. And notice we do it in the opposite order. Just like when we undo an equation to solve for x, it's like anti-BODMAS. We go the opposite to BODMAS. So add 1 to the power, it's 3x to the 5, and then divide by the power. So we're dividing by 5, so that's how we get 3/5 x to the 5. So let's actually do the question now, and obviously we don't have to do a flow chart every time we do that. Let's try and delete that bit. There we go. So now let's actually do the examples, and we've got 3x to the 4, so that's going to be 3/5 x to the 5, as we did in quite extreme detail. Now we x to the power of 3, it's going to become x to the power of 4, and we're dividing by 4, so it's 1/4 x to the 4, and then plus 2 x to the power of 0, this is 0 plus 1 is 1, 2 divided by 1 is 2, so it's 2x, and we then put a plus c at the end. And you might remember as well from last year that we need the plus c because when we differentiate, like just say we had, we'll just say we have this. Let's pretend it's not part of that. And we say we want to find the derivative of this. Just say this is y equals. And let's pretend there's a plus 10 on the end. Well, if we differentiate that, you're not going to get the 10. There's going to be nothing to do with the 10 here. So there's no way that you can get back to that 10 if you anti-differentiate. So the point is that we don't know if there's a plus 10, a minus 50, a plus 0 at the end. Who knows what is at the end? So what we do to indicate that we don't know what's at the end, we put plus c, and c is the constant, and whatever that may be. So there would be our answer to the first one. Let's move on. And look, this is not a more difficult one in any way. It's just that it includes a root and it includes a negative power. So what you want to do is always write it out in one line where possible. So of course, root means power half. And 1/x² is x to the power of -2. So now it's saying find the rule for f. So that means we're just anti-differentiating it. So we can say add 1 to the power. So let's say 2x to the half plus 1, which is 2/2. And we're dividing by the new power, which is 3/2, plus x to the -1. Be careful, because a lot of people are going to say -3 there. But -2 plus 1 is, of course, -1. 7x to the 0 plus 1/1. So now let's neaten that up. Now, this part, we've got 2x to the 3 on 2, whoops, 2, not 3 on 3, we're dividing by 3 on 2. So, of course, when we divide fractions, we're multiplying by the reciprocal. So we're going to be getting 4/3 x to the 3 on 2. And then we've got minus x to the neg 1, which, well, that can go into the denominator. So there's 1 over x minus 7x, and of course plus c at the end. So don't forget the plus c, because it's saying find the rule. So we don't know what c is. Sometimes they'll say find an antiderivative, which actually is coming up next. If it's an antiderivative, the c could be 0, so you don't need to include the plus c. But if it says find the antiderivative or find the rule for f, you do need to include the plus c. So I think the main things there were working with the fraction, the dividing by the fraction, which isn't hard, but still just something to think about. And of course, remembering the plus c on the end, and putting this into this form to start. The next one, so find an antiderivative of this. So this is the one where we won't need a plus c. So I'm going to expand this. 2x times 4 is 8x. 2x times neg x is negative 2x squared. Neg 3 times 4, neg 12. Neg 3 times neg x plus 3x. Let's collect like terms. So we've got neg 2x squared minus 8 plus, no, sorry, not minus 8, 8 plus 3 is 11. And minus 12 dx. So don't forget the dx at the end, and this. And well, that's going to equal negative 2 over 3 x to the 3 plus 11 on 2 x squared minus 12x. And as I said, we don't need the plus c because it's an antiderivative. So an antiderivative, I could put plus 100 here if I want. That's an antiderivative, but it's kind of weird. You would be far more likely to just leave it as plus 0, so you don't put anything on the end. So there would be our antiderivative. All right, moving on. Let's go to, there's another one. Oh yeah, a little bit small, this one perhaps. Okay, so this one here, you might think, oh, it looks like it could be something with a quotient rule, because in differentiation we have a quotient rule. You might think, oh, well, there must be an anti-quotient rule. No, there isn't. So in any case, even if you were doing a differentiation, you would always try and simplify things into one line rather than use a quotient rule. It would be a lot easier, and that's the same here. So I'm going to make this into x to the 4 over x to the 3 minus 2x3 over x to the 3 plus 5 over x to the 3 dx. And of course, that's going to be x, so 4 minus 3 is 1, minus 2, and then x to the 3 over x to the 3, they will cancel, plus 5x to the neg 3 dx. And then you see now it's quite straightforward to be able to make an antiderivative. So this is power 1, so I'm adding 1, so it's going to be 1 over 2 x squared minus 2x minus 5 over 4 x to the neg 4. And, oh no, neg 2, what have I done? That was silly. So, so minus 5 over 2, because of course negative 3 plus 1 would be negative 2, not negative 4. That's just actually a common silly mistake, so be careful of that. So that goes to the power of negative 2, and we are looking for just the antiderivative, so I need a plus c. I will now neaten that up simply by putting this into the denominator, and I'm just going to rub it out and put it there because I'm running out of room. So there would be my antiderivative, taking into account that we started with something that had a fraction and I made it into one line before I antiderived it. Another thing I think is really good when you are doing something that requires you to change its form. This is the same for differentiation, like if you have roots or you have things in the denominator. I would write this on every line until you actually do the antidifferentiation, because sometimes people will do all this working out and changing it and then forget that they haven't actually anti-derived it at all. They've just changed the form. And as I said, the same applies for differentiation, which we've already discussed. Okay, so look, the next type is where we have something that if it was differentiation, like if we were differentiating something like this, we would use a chain rule. The same if it was something like this, we could use a chain rule. We don't have an anti-chain rule, we have this. And we need to know how to anti-derive using this formula. In the Cambridge textbook, they write it slightly differently, and it's the same thing, but I'll put it here just in case you prefer it. All it is that they put it as 1 over a n plus 1, and then they put the ax plus b to the power n plus 1 plus c. So it's exactly the same thing. There's really absolutely no difference, only that they've just look slightly different. So they've just taken this out and the 1 in the numerator. So I actually prefer writing it like that. I think probably because I used Cambridge for many years before using Jack. So I'll use that form, but there's no difference. So at the moment we've got 2x plus 3 to the power of 5 dx. And really you just have to correctly identify a and b. And well, n, but you can't go too wrong there. There's a to the power of n. So then we just put the values in. 1 over 2, n plus 1, 5 plus 1 is 6. And then ax plus b, so it's the same thing that's in the brackets. To the power of n plus 1, so that's 6. So we get 1 over 12, 2x plus 3 to the 6 plus c. And I mean, you could put the 12, like the denominator of 12 over everything if you prefer, and using the jacplus formula, well, that's what you would get. But I mean, really, it doesn't matter. Either way is fine. So there it is. Don't forget the plus c on the end. There's another one like that. Now, this one has a 2 out the front, which really doesn't make it any more difficult, just that some people don't know what to do with the 2. So if you take the 2 out, it's just a multiplying constant there, and then we've got 3x minus 1 to the negative 2 dx. And then we can say, well, that's going to equal 2 times 1 over a, which is 3, n plus 1, n is negative 1, no, it's negative 2, plus 1, ax plus b, 3x minus 1, negative 2 plus 1 is negative 1, and plus c. So let's neaten it up. So 2 over negative 2 plus 1 is a negative 1. So it's going to be negative 2/3. 3x minus 1 to the negative 1 plus c. And look, you would be better off to write the negative power into the denominator there. So there it is. So really, it's not hard. Just be careful. I don't think they give us an example like this, but I know they have them in the book. Be careful if it's something like, oh, what's going on? If it had like 3 minus 2x. So I mean, it's not hard, but it just means that, well, your a value is negative 2. The a value is the thing in front of the x, not the thing that comes first. So just be aware of that. Also be aware, at first I wrote a 2 here, but then I was like, well, we wouldn't use the rule if it was squared. If it was just squared, you would expand it. It would be a lot easier to expand than to use this rule. Let's move on. Here's one where people might think, oh, we'll use that rule. No, you would not use that rule. You would just expand this. So that's what I'm talking about, what I was talking about then. So this you can say is x plus 1 over x times x plus 1 over x. But it would be better if you identify it, because that would require to FOIL it. It would be better if you identify it as a plus b squared is a squared plus 2ab plus b squared. And really, I mean, you should be very good at those identities by now and be able to use them really easily. So a is x and b is 1 on x. So that means we've got the antiderivative of x squared plus 2ab plus b squared. And again, notice that I'm writing this at the start and the end, because then I don't forget that actually I haven't anti-differentiated anything yet. So this will cancel, so it's plus 2 plus 1 over x squared, and I'm just going to write that as x to the negative 2. So sometimes people will write that as their final answer because, well, you've done all that work, but actually that's not the antiderivative at all. So as I'm saying, if you write this at the end and the start of each line, you're unlikely to forget. So now let's antidifferentiate, and that's going to equal 1/3 x cubed plus 2x. Negative 2 plus 1 is negative 1. And when we have x to the negative 1, we can write that as 1 over x. So that will be our antiderivative. And again, notice that I have put plus c on the end. Really be careful, you need to put plus c where it's required. The only time you don't, if it says an antiderivative, or of course if we're finding an actual function, they give us a point to sub in, which I believe is in 7.3. We'll do that. All right, last one, and I like jacplus for these type of questions. So this is deriving by inspection, or there's another word for it which I've forgotten, but in any case, it's in jacplus they introduce it to us quite slowly, so we can work with some easier ones before going to the more difficult ones. It's quite good. So I'm going to cross out this part of the question, because if this was a question on a SAC or exam, there would be at least a mark for finding the derivative. So some people will leave it blank because there's just too many words there. So the first part, if y equals 3x squared plus 4x minus 7 to the 5, find dy dx. So let's just do that as on its own. So let's say let u equal 3x squared plus 4x minus 7. Therefore, y equals u to the 5. So as you can see, we're just using basic chain rule, which we always do. And we know the chain rule, dy dx is dy du times du dx. And, well, dy over du is going to be 5u to the 4. And du over dx, so actually I shouldn't put that in brackets, is going to be 6x plus 4. So I have done du, the derivative of u with respect to x comes from that, and the derivative of y with respect to u, derivative of y with respect to u comes from that. So now we can multiply them together. So dy dx equals, let's say 6x plus 4, and then u, what was that? 3x2, or 3x squared, I should say, plus 4x minus 7 to the power of 4. All right, so there's my derivative. I might take out a 2 here. So, if I take a 2 out, I get 10, 3x plus 2. I've got 3x squared plus 4x minus 7 to the 4. Okay, so now that I've derived that, it's got to be that the next part of the question has something to do with that, and is in fact quite similar to that. So let's just make it a little smaller so we can see, and let's delete that. So now let's go for this part. Okay, so let's see what's the same. And this is the key to getting these right, identifying what's the same and what's different, or what you have to change. So I've got 3x plus 2, there's that. And I've got 3x squared plus 4x minus 7 to the power of 4. So really everything's the same, except I've got that 10 there. So we just said, we've now got a derivative. So we said that we went from y and we derived to get dy dx. Oops. We derived. So if we derived y, to get dy dx. It means that to go backwards, we would antiderive. We would antiderive dy dx. So I'm just going to write that. And so if I antiderive the dy dx, well, that would mean that I get back to 3x squared plus 4x minus 7. It's about 5. So when I derived that, I got that. Now, if I antiderive the answer to the derivative, then I go back to what I had. So what I can do now is I can say, well, for a start, I can take this 10 out. Let's do that. Equals nearly there to the 5. Okay. So what I want to antiderive is not this. It's actually very similar though. So let's just choose a different color and write it underneath. I believe it was 20. Let's double check that. Yes. So and we want an antiderivative for that. So if we've got an antiderivative for this, we know it's 3x squared plus 4x minus 7. Well, then we just need to see what we need to do different. What's different between the two? And I'll tell you what's different between the two. There's only a 10 here and there's a 20 here. And we can say, well, to get from 10 to 20, we can multiply by 2. So, you know, if we multiply on the left by 2, as you know from like year 8, you have to, what you do on one side, you do on the other. So we multiply by 2 here as well. So it's actually really quite easy. We just multiply that answer by 2. And that's our antiderivative. So I remembered what it's called. It's antiderivation by recognition. So we recognize that the two equations are very similar. You know, this one in the green, it's very similar to what we have when we're trying to antiderive the blue there. And we just need to change it in one small way here. And that's what we've done. So these get harder as we go through this chapter, and it's quite important to work through the easier ones, because then you really start to see how they work rather than just going straight into the hard ones later on. I believe that's it for the worked examples. Yes, it is.